We worked that problem yesterday during the homework session with the drag car. I was fairly intrigued by that problem. I thought that was an interesting problem. I wanted to go through it today. We'll work it in some more problems, but I'll go through this in a little more detail. So a lot of this is laid out in your homework problem. I'll also be posting these PDFs. Okay, so if you don't want to write all this down, that's fine. I looked at this drag car. The first case I looked at, and we did this last time, would be if it was pulled the front wheels up off the ground. So I've kind of exaggerated the drawing, and then I've gone back and assumed that this angle is very small. So everyone can see that those front wheels are pulled off the ground, but we're probably looking where the wheel is actually down here, much closer to the ground. We're going to say that this angle in here is very small, about 0. Okay? So then when we go through it, and in the homework solutions, you saw this equation being used, and you saw that equation being used. So I wanted to go through both of those. Well, I used sum of the forces in the vertical is equal to mass times acceleration in the vertical, and then sum of the forces in the horizontal is equal to mass times acceleration in the horizontal. So I came up with an equation here, and then I plugged this value for the rear reaction back into this moment equation, and I came up with the tractive force. Not necessarily the friction force, but the tractive force. And then I came up with a tractive force, and then I was also able to find the acceleration. And likewise, if I used this equation over here, I just found the acceleration directly. So maybe in this case, this acceleration was actually better. The one thing we certainly would not want to do would be to say that the sum of the moments about some point O is equal to I about O times alpha. That wouldn't be allowed because the stipulation on that equation is O is not accelerating, right? And all the points on this are accelerating. So we went through this last time. We came up with the acceleration. It'd give you a really high acceleration, 21 meters per second squared. That's about what, 2g? Okay, when we talk about g's, that's about 2 g's. So then we looked at the other case, and the other case, instead of it doing a wheel stand, instead of it pulling the front wheels off the ground, it's just on the verge of breaking traction here. So you'll see that in this previous case, when I had the wheel stand, I talked about the tractive force, and I didn't say that that was equal to the coefficient of friction times mu, because it's not. It's probably not up to that value yet. And here I'm going to say that the friction is fully developed, and I have mu times the normal force at the rear. I didn't look at the four-wheel drive case like your homework problem did. I just looked at the rear case, and I'm going to go into this in some more detail. But I used, again, some of the forces in the vertical, some of the forces in the horizontal, and then I used my sum of the moments about g. And you could, if you wanted to, come back and use this equation. Probably in this one, that equation is probably, again, a little bit easier. So I think we came up with these values, and we came up with a much smaller acceleration, and then we had to try and rationalize that. Would we be able to get to that 2g acceleration if our maximum acceleration based on friction is only, what, a fraction of a g? We wouldn't, would we? We'd start to break traction. We'd start spinning the rear wheels a long time before we pulled the front wheels off the ground, right? And I'd mentioned that the coefficient of friction, 0.2, is very low. That'd probably be, the track was iced up. So I started to play around with that, and I said, what if, here is the case where, set that aside. Here's the case where the coefficient is 0.2, and I built this matrix, and I solved for exactly what we saw in the last problem. This just went through this with a matrix, so I could change the numbers a little more quickly than having to go through each one. So that's exactly the same calculation that we had. So what I said then was, what happens if mu comes up to about 1.25? I did a little bit of research, which means about 30 seconds at Google, and it looks like for drag tires, they get pretty high coefficients of friction, which makes sense. They usually are doing this in the summertime when the track is fairly hot. They've got a whole process of burning them out to make them sticky and whatnot. So I think the numbers probably actually go higher than that. We'll address that. But I said 1.25, which seems like kind of an odd number, but for this case where you can have something that's sticky, it may not be that odd. We came up with an acceleration that was, interestingly enough, what's that? That's about g, isn't it? 1g. Okay. We noticed that the front reaction is still fairly good number, fairly large number. We've got some weight on that front axle yet. So I decided to continue to play around with the numbers, and this is just a repeat of that at 1.125 coming up with the acceleration there. So I said, what happens if I have 2 1/4? And I was actually looking at they were saying the numbers were running, some of them were saying as high as 5, which seemed like an awfully large coefficient of friction. But I decided, well, I'll put 2.25 in here, and came up with a fairly large acceleration. In that case, we would have pulled the front axle off the ground, right? Because what was our acceleration for the front axle? 21? Wasn't that what that was? So, yeah, 21. So we're going to pull the front axle off of that. So we would have pulled the front axle off the ground, which makes sense because what do we notice here? Yeah, we have a negative reaction at the front, which means we would have pulled the front axle off the ground. So this is really kind of nonsensical because of that. Unless we have that front axle in some sort of a track, that's probably not going to happen. Okay, so I decided to tone down this friction number a little bit. And so I played around with the number here and came up with something that was pretty close to, what, 21.0. And we came up with this was pretty close to 0, right? So we're back to the example where we just pulled the front wheels off the ground. So, what's that? I put a coefficient of 2.14. Okay. A few, which it looks like they're getting numbers about that high. So kind of an interesting problem when you go through it. So I didn't tackle a four-wheel drive part. You could go back and do that on your own if you wanted to. But it's kind of interesting as you try and get more of the weight onto the back axle. So, questions with that? So I guess that print got a little small. If you, I'll be posting these PDFs. Well, I wanted to tackle a couple more problems here, conceptual problems that sometimes give students trouble. Hopefully these will be a little easier to see. We've got something that's rolling along, so we'll talk about that a tire or a disc or a cylinder that's rolling along. And let's say that it's rolling like this with some omega, and we have some no-slip at the bottom there. Okay? So we've got no slip. And the question comes up, what's the velocity of A with respect to B? So you, imagine yourself possibly as an observer at B looking at something at A. So you have a flag down there or something at A, and you're watching it from a position at B. So the velocity of A with respect to B. I mean, if it's a tire rolling along, that's probably kind of silly, but if it's a large disc or something, standing at B might make some sense. Well, one way to think about this is to look at this, go back to our vector equation, and say that the velocity of A is equal to the velocity of B plus the velocity of A with respect to B. We've used that before. If I solve for the velocity of A with respect to B, couldn't I say that that was the velocity of A minus the velocity of B, right? Hopefully that's fair enough. So if I look at this thing, and I will redraw this thing rolling along with no slip at this point, that's our instantaneous center of zero velocity. It's rotating about that point, isn't it? So if I take this perpendicular to B, where's the velocity of B going to look? If it's going like this, the velocity of B is going to look something like that, isn't it? Okay. Whereas if I look at the velocity of A, what's the velocity of A? I'm going to do something like this, and I will have the velocity of A. Okay. And if I draw these to some scale, maybe I should make the B one a little bit larger, right? Because isn't the R distance, this distance here, which would be the diameter of that circle, this one is less than that. Maybe I'll just say less than the diameter, right? So that distance is less than that distance, so we'd expect the velocity of B to be greater than the velocity of A, wouldn't we? And we'd have those rough directions. So let's put that into play here. I could say, taking the velocity of A, I have something like this. And then I need minus the velocity of B. Well, if this is the velocity of B, what's minus the velocity of B? Same thing, but in the opposite direction, right? So I get something like this. There is minus the velocity of B. There is the velocity of A. So if I take the velocity of A and subtract the velocity of B, I have that as the velocity of A with respect to B. So a bit unintuitive, but if you go through this process, quite rational. Questions with that? So something good to think about there. No questions with that? Let's try one more problem. So let's say someone's given us a disc or a flywheel. This just goes into the page a little bit. Okay, and we've got this centroidal axis, and it's rotating about that. You could imagine maybe this is on some shaft, and it's going to rotate about that. And we'd like to find the I about that center line. Okay, so which one of these is it? So with something like this, we'll go to our table of shapes. I mean, we could go back and derive these, but standard shape, and we don't want to spend the time when we don't need to. I think we can recognize that it's not a thin rod. It's not a thin ring. Then we might have some trouble trying to figure out, well, is it a cylinder or is it a thin circular disc? Well, the nice thing is we don't have to worry too much about that, because through this ZZ axis here we have 1/2 mr squared, and through the ZZ axis here we have 1/2 mr squared. So it looks like our what we're going to be using is that I is going to be equal to 1/2 mr squared. Now, before we head back to the problem, a couple notes. When you look at getting ready for the final and whatnot, I will make sure that this table is available to you on the final. And just like with this problem, you're going to have to figure out which one you need to use and which direction you need to use, and maybe even have to use the parallel axis theorem to sort it out. The excuse me. The other thing is I wanted to again mention that if you're looking in the cover flap of some of the older editions of the textbook, a couple editions back, they actually made a mistake on either this one or this one. I don't remember. So double check that. I've checked this. This is correct, and this will be available to you on your final. So with that, we can head back to the problem. So I will say 1/2 mr squared. We're told this thing has a weight of 100 pounds. And the reason I'm doing this is most of the time up to this we've done a metric problem, which is probably a little easier with the units and whatnot. So I wanted to tackle this so that no one got burnt on the units on this thing. So we got 100 pounds here. We got a diameter of 18 inches, right? Isn't that the symbol for diameter? It's either that or the electrical folks are saying 18 phase. Okay. So, got to read it in context. So we've got 18-inch diameter, which would mean that 9-inch radius. So let's see how this works. I'm going to be probably more careful with the units since this is an English problem. So I've got 1/2 times 100 pounds, and that is a weight, isn't it? So I need the mass. I'm going to divide by 32.2 feet per second squared. And then I have to multiply this by the radius. Now I know that the radius is equal to 9 inches. Divide 18 by 2, you get 9 inches. But if I'm working in feet here, I'd better do what? Divide by 12 and call this feet, right? So I'm going to say that this is 9 over 12 squared, feet squared. Okay. So I guess I could run through the math here. Anyone come up with 0.873? Anyone get that number? Few people? Great. Okay, good. Okay, so the calculator works. And then what do we have for units? We're going to have pounds, and one of these gets canceled with that, and the denominator becomes a numerator, so I come up with this pounds times feet times seconds squared. Okay, that's actually right. Okay, if you want those base units. If you wanted to, you could then multiply this by 12, and you would come up with some answer, multiplied that by 12, and it would be pounds, inches, because this is 12 inches in a foot, pound, inches, second squared, which would be right. Okay. Now some of you might be saying, well, this seems weird. We said that this was going to, in general, would have units of mass times distance squared, right? So let's see, mass is slugs times feet or inches squared. Why don't we say feet squared? So we'd expect feet, slugs, foot squared. This is not slug foot squared. Well, let's deal with that. If we go to Newton's second law, force is equal to mass times acceleration, we would have then that a pound would be equal to a slug times the acceleration of a foot per second squared. So we can say then that a slug is equal to a pound times second squared divided by a foot. This is just getting more fun as it goes, isn't it? Okay. So what if I take this unit that I have here, going back to this one, and so I take a pound foot second squared, and I multiply that by a foot over a foot, which seems weird, but I can multiply by 1, can't I? Foot over a foot, there's 1, so that's fair game. So this turns out to be a pound times a foot squared times a second squared divided by foot. Well, what did we say that a slug was? Pound second squared over a foot. So pound second squared. So I have a slug foot squared. Okay. So this is really a proper unit, kind of an odd unit. You could put it in inches. That would be a proper unit, kind of an odd unit. This is probably what you're expecting. Okay. So I just wanted to spend some time talking about those units because we hadn't necessarily done too much. We did the metric system. We started in the metric system, which is probably prudent, a little easier to deal with as we get going. But you'll see things come up in the English system. You have to be able to deal with that. Questions with that? Okay. So I think the request for today was to work a few problems from the final. I have. Okay. I think that's it. So I guess we got to the end. Maybe we should do this. This is page 10. So what? That would be page 11. We don't want people showing up for spring break. I guess I need a big marker, don't I? I got a big marker here. Yeah. That was page 11. So anyway, make sure you show up for the final.